Hey everybody, welcome to today's lesson. We're going to be talking a little bit about hydrates. This is really an extension on our empirical formula lesson, and I just wanted to introduce you to hydrates since we will likely be hopefully doing a lab that involves hydrates. So what is a hydrate? Well, if you look at the base of the word hydra or hydro, right, it makes you think of water. And that's because a hydrate, okay, by definition, is going to be a compound in which water molecules are trapped inside. Okay, so we have these ionic compounds, and within those compounds, water molecules are trapped in the crystalline structure. And so, I have an example here of a hydrate that I think is particularly cool, okay? And the reason I think it's really cool is because we've already talked a little bit about transition metals and how transition metals create colored solutions, right? Or when a transition metal compound is dissolved into water, it will create a beautiful colored solution. Here, though, we don't have a solution per se, but we have a hydrated compound that contains a transition metal. And so this beautiful blue right here, this is a hydrate, okay? And we know that it contains that transition metal because it's a beautiful blue color. It's likely a copper hydrate. I didn't specifically look at which one it was, but this is the hydrated substance. You can see it still has that crystal structure, and within those crystals are teeny tiny water molecules trapped inside. It doesn't feel wet, it doesn't look wet really, it looks like a regular crystal, it just has water trapped inside. And what will happen is if we remove that water from that, we get what's called an anhydrous, or without water, substance, and that would be this example here. This is considered anhydrous, or it has the water removed, or it's without water. And you can see that it's lost that beautiful blue color because, again, without water present, those transition metal ions are not going to present in a colored way. And so we have our hydrated salt and we have our anhydrous salt. Okay. Now, what is a hydrate? How would I recognize if a substance is considered hydrated? Well, we actually ran into this on the Calculating Gram Formula Mass worksheet that I assigned, and I had a lot of people asking me, well, what's that dot, Miss Daly? What does that dot really mean? And so a hydrate is going to be represented like this, okay? So we have our ionic compound, for example, copper 2 sulfate, and when you see this dot symbol there and a amount of water, what that represents is that it's actually a hydrated substance, okay? And so that dot right here, it does not mean multiply. All that dot means is that there is water trapped inside. Okay, it does not mean multiply, it just means water trapped inside. And so if I'm looking at this, what this really reads at is for every 1 copper sulfate or copper 2 sulfate, I have 5 water molecules trapped inside of that 1 copper sulfate. Now, how do we determine the ratio of copper sulfate, for example, in this problem, to water? Okay, how many moles or particles per each? And the answer comes with the empirical formula like we've been practicing. So I do want to quickly, briefly just go over kind of the laboratory setup that we would see for this and how we would go about doing this, which is going to be using what is called a crucible. So I'm going to go ahead and insert that image here of the crucible. Okay, so that you guys can see what that looks like. And so here we have our lab set up for what would happen. Now, in order for us to determine how much water is trapped inside of our hydrated sample, we need to take the initial mass of our hydrated sample, what's called drive off the water, also known as just remove the water by heating it, and then take the mass of our anhydrous sample. And from there, we can figure out the mass of the water that was trapped inside. Now, in this lab, we would use what's called a crucible. It's typically a porcelain a porcelain little dish with a little cover that allows us to heat the substance. And excuse me, and we would use a Bunsen burner to heat that substance. So if you're following along on my guided notes sheet, I've given you a set of sample data that we're going to use to calculate the ratio of an ionic salt with water. But if you're not following along, let me put that data here. So in a lab, a student heated a calcium chloride hydrate until all of the water was driven off. Again, driven off means just removed. The student collected the following data. The mass of the hydrate prior to heating was 4.72 grams. And then the mass of the anhydrous, remember that means without water, okay, was 3.56 grams. So to determine the mass of water that was in the initial sample, we're just going to simply subtract 4.72 minus 3.56 to find the mass of the water, which is going to give us 1.16 grams. Okay? Now, using the student's data, I want to determine the mole-to-mole ratio, which should sound really familiar from empirical formula, okay, of anhydrous calcium chloride, CaCl2, and water, and then give the formula of the hydrate. So essentially, what we're trying to do here is figure out the ratio of CaCl2 to how much water is present. I want to know these two mole-to-mole values. So when I said it's an extension of our empirical formula lesson, it's because the calculation is pretty much exactly the same. So what we're going to need to do is we're going to need to go through our step-by-step percent to mass to moles divided by small multiplied to whole poem. Now, in this specific example, notice that we're already starting with masses. So for step number 1, which is, again, percent to mass, we can already skip this problem, right? We're already starting with masses. We don't need to go ahead and convert from percent to mass if we're already starting with mass values, okay? Step 2, though, which is convert to moles or mass to moles, okay, we do need to complete that. So step number 2 is mass to moles, okay? And so for this, we want to go ahead and convert the moles of CaCl2 that we have and the moles of water that we have. Now, before we can do that, we do need to calculate the gram formula mass of both water and of calcium chloride. So let's go ahead and take a moment just off to the side here, and let's calculate the gram formula mass or the molar mass of both water and CaCl2 calcium chloride. So for water, we have H, we have O, we have 2 H's and 1 O. And we're going to multiply those by their atomic masses. Again, I like to round to the hundredths place. And this is going to give me a total of 18.02. And again, units are grams per mole for water. And for calcium chloride, I have Ca, I have Cl, 1 Ca for every 2 Cls. Ca's mass is 40.1 grams per mole or grams, and Cl is 35.45 or 5 grams. Let's just round it to the tenths, I guess, for simplicity. And that's going to give me 40.1, and that's going to give me 71.0, giving me an overall gram formula mass for calcium chloride of 111.1 grams per mole. Okay. From there, we're now going to go ahead and convert these values into moles. So let's go ahead and do that. So again, mass of the CaCl2. Where do I find that for my problem? So again, our mass of our hydrate up here is really CaCl2 plus H2O, okay? Our mass of our anhydrous means we've removed the water, which means this is just the mass of the CaCl2. And the mass of the water is obviously just the mass of the water, okay? So first, to convert the water, okay, we have our mass value. So for H2O, okay, I have 1.16 grams, okay, and I need to convert that to moles. So in order to do that, we do X moles equals 1.16 grams divided by 18.02 grams per mole. Okay, and from there we're going to calculate that out, and we get a total of 0.06 moles. Okay, for CaCl2, okay, we have again our initial starting mass, which is our anhydrous sample. So that's going to be 3.56 grams, and we're going to convert that to moles. So we get X moles is equal to 3.56 grams divided by 111.1 grams per mole. And that's going to give me a total of 0.03 moles. Okay, so now we have our mole values of each. And again, our overall goal of this is to determine the ratio of anhydrous CaCl2 to the ratio of water trapped inside. So in order to find the ratio, we need to complete step number 3, which is going to be to divide by small. And so for water, okay, we had 0.06 moles, and for CaCl2, we had 0.03 moles. We're going to divide by the smaller of the two values, and that's going to give us 2 waters for every 1 calcium chloride. And again, there's no multiply by small here, just because we're already at a nice 2-to-1 ratio, there's no need to multiply. So that's going to be our process of finding the empirical formula of how we do that, or how do we find the ratio of water to anhydrous in a hydrated sample. But how do I go ahead and now write that into my formula to represent that hydrate? So we're going to go back to, again, that initial thing that I had, which was we're again figuring out the ratio of CaCl2 to the water molecules. And so our final answer here is going to be, for every 1 CaCl2, I have 2 H2O. And this is the formula of the hydrate. Okay, so again, I do want to just be really clear here. This is not a multiplication symbol. All it means is that those water molecules are trapped inside. All right, everybody, I will see you guys tomorrow in class. Have a great rest of your night.